Welcome back to the series of lectures on high performance scientific computing. So far we have been looking at how to profile serial codes, how to profile parallel codes, and how to actually look at parallel code performance on distributed memory machines, which basically use MPI. One of the factors that which we had mentioned in one of the previous videos is how the algorithmic efficiency is a key parameter in trying to achieve scalability. So we might have the best sort of hardware, the best CPU cores, the best communication devices, everything, but there could be certain bottlenecks in the algorithm as well. So in today's video, we will look at a specific case study to see what happens in scientific computing when we have to make algorithmic or changes at the numerical method level, and what drives these changes. So one of the key things is that there has been a tremendous growth in supercomputing power over the last few decades. This is something which we had touched upon in the initial few lectures as well. Here is a plot of the fastest supercomputer in the world from the years 1993 to till 2014, and this trend has been increasing till current years as well. So you can see the red line is the fastest supercomputer, the yellow line is a 500th fastest supercomputer, and the blue line is the aggregate power of all these 500 supercomputers. And you can see this is growing at an exponential scale. The question that we need to ask is, once we have the exaflop machines, so we have exascale machines today. Frontier, which is at Oak Ridge National Labs, is the first exascale machine which is able to do 10 raised to 18 floating point operations per second. The questions we need to ask are, is there a need for exascale computing? What sort of problems we're going to solve for this exascale computing? Clearly, there are many problems in the world that which we can use, from climate prediction to modeling advanced multiphysics of nuclear reactors, so on and so forth. We also have to wonder what will be the architecture of these exascale machines. But more importantly, we need to ask whether the current numerical methods and scientific computing techniques that we have are adequate and scalable when it comes to these exascale machines. Forget exascale machines, are they even scalable for existing petascale computations, which is 1,000 orders of magnitude less? So we need to ask these questions to see if we are using these large machines efficiently. So one of the prizes that is awarded is something called as a Gordon Bell Prize, which is given to the largest scientific compute over the years. One thing which is noticeable is that for every year, the size of the problem keeps on increasing, but you can see that the efficiency of these problems at which they are scaling is actually dropping. So you can see that in 2012, it had only about 42% efficiency. So we really need to answer the question of parallel scalability and parallel efficiency when we are writing these large codes. So now we will look at a mathematical perspective of one particular case study to see how designing efficient numerical methods actually plays into the role of developing scalable and efficient algorithms. So we will now have a basic introduction to certain numerical methods at a very broad level, and then we will see how this plays into the numerical method, into parallel scalability and parallel efficiency. Now, if you look at most numerical methods, right? So you have certain governing equations which is describing some sort of physical phenomena that you want to understand, but they cannot, these governing equations, which are in the form of partial differential equations, they cannot be solved analytically. So we typically have numerical methods which provide solutions. That's why we use these modern computers for simulations. Now, the process of representing these partial differential equations as a set of algebraic equations which have equivalent properties is called discretization. And then there are several numerical techniques for discretization, some of which have been popular over several decades, like the finite difference method, finite element method, finite volume method, continuous Galerkin, and discontinuous Galerkin. There are several techniques for it. So one of the things that we need to understand what are the properties of good numerical methods. One is it must be consistent with the continuous problem. What do I mean by that? I take a set of continuous partial differential equations and then I discretize them over a discrete set of points. And once I discretize them over this discrete set of points, I get a set of algebraic equations. Now, if these discrete set of points, the distance between them starts tending to 0 and in the limit of it tending to 0, the set of algebraic equations which I have created, they must recover back the original partial differential equations. That is the meaning of the numerical method being consistent with the continuous problem. It also must be stable. So whenever we discretize a problem, we take a continuous partial differential equation and convert it into a series of discrete algebraic equations, we introduce numerical errors. Now these numerical errors are usually proportionate to the size of the discrete interval that we are taking. When we say the method must be stable, is that as the solution evolves, these errors must be finite and bounded. They cannot grow in an unbounded fashion. We are not saying that the error should go to 0. We are saying that the error should be bounded and remain finite. If the error remains bounded and finite over the time of the calculation, then the method is said to be stable. And obviously, if the method is consistent and stable, then it will converge to the correct solution, albeit with some errors. So that's fine. So these first 2 points are an absolute essential for a numerical method. Without these, you cannot use any of these numerical methods in a consistent way. The next 3 points are sort of desirables and hopefully should be there for all other numerical methods. First of all, it must be as accurate as possible. We have clearly mentioned the fact that the numerical method will introduce some error. We want to minimize this error as much as possible. 2, it must be computationally efficient. It cannot take too many computational cycles to produce the result, because there is no point if a method is consistent, stable, very accurate, but computationally inefficient, which cannot give us reasonable results in a cheap and efficient manner. Finally, it also should be geometrically flexible, because most of the problems that we try to look at least from the engineering sense, has very complicated geometry. If a method works only in certain specified geometry, like say only quadrilaterals or hexahedra, or only in circular domains or spherical domains, then it's very useful, only the use limits are very few for it. So it is good to have a method which is also geometrically flexible. So typically this is the method. We have some sort of generalized conservation equation with some variable phi. We have a temporal derivative of the variable. We have the convective flux. We have a diffusion term, and we have a source term. If you look at the finite volume method, it discretizes the conservation equation by integrating it over a small controlled volume and over a finite time step temporarily. The control volume is denoted as V and the time step as delta t. So if you look at the polyhedral finite volume method, the computational domain is now divided into several computational cells which form control volumes over which the governing PDEs are discretized. The control volumes can be arbitrary polyhedra in 3 dimensions, so that gives us geometric flexibility. the computational cell or control volume can have any number of faces. It provides geometric freedom and it enables the resolution of complex geometries. If you look at a typical finite volume stencil, this is how it looks. Now, if you are at the black point, then you need to evaluate, say, higher order derivatives. You start taking information from your neighboring points. If you want information with higher orders of accuracy, you have to keep taking more and more information from your neighbors. Now, let us say we discretize this problem and the cell denoted by the black circle happens to be near a CPU boundary. Then the information that it needs is to compute the higher order derivatives is now going to take the information from neighboring processes or neighboring CPUs. That means it will have to do some sort of communication. In a distributed memory sense, it will have to do MPI sends and MPI receives, which we know are usually bottlenecks. The higher order accuracy that I need, more is the communication that I need to do. So this then causes problems with scalability. So typically, once we express the system in a matrix form, we look at the problem in terms of an AX is equal to B problem, where we then try to figure out what X is through a set of linear algebra calculations. Now, this is the sparsity pattern for a typical finite volume stencil. And we can reorder the matrix a little bit to improve the communication, but you can still see that you have a very wide communication stencil. That means I have to take information from further away every single time I try to solve this problem. Now, this is a problem for both serial and parallel computations. The reason being, typically in stencils like this, the information I need is not local to me. So if I'm doing a serial calculation, there's probably not local in cache. If I'm doing the calculation in distributed memory machines, that means I have to do more MPI calls to get the relevant information I need to do my compute. And typically, this results in scaling problems. This is the parallel scaling of OpenFOAM, a very popular open source code for doing finite volume calculations. And here, this scaling study done by a university in Norway shows how does the code OpenFOAM scale. You can see the ideal speed up is denoted by the light yellow line, and you can see that the scaling sort of peaks at around 2000 processors to about 200 processors depending on the size of the problem. So if you have a small problem of say only 1 million cells, then you do not get scaling beyond about 250 processors. If you increase the size of the problem, say to up to 27 million, you get to see scaling efficiency up to only about 2000 processors. We had said initially that today's modern machines can have up to hundreds of thousands or even millions of processors. So what is the takeaway that we have? The takeaway that we have is that this particular code or this particular numerical technique cannot exploit the maximum resources of today's modern high-performance computing machines. There's another curious question here you will see is that in the initial part of this scaling study, that the speedups are showing super linear scalability in the sense that they seem to be working at more than 100% efficiency. This is because of the trick of strong scaling where you're reducing the number of degrees of freedom per processor as you're increasing the processor count. It becomes more and more cache efficient and things start fitting into cache and in lower levels of memory. So that's why when you're using the baseline of a single processor where it's not as cache efficient, you start seeing superlinear scalability. So this superlinear scalability is not an error or a weird artifact. You actually get to see this because of cache efficiency. Now let us start talking about a little bit more of more efficient numerical methods. So we will now discuss what is element-based Galericon methods. Element-based Galericon methods partition the domain into computational elements and then they approximate it using basis functions. If you use C0 continuity in your solution, then you have continuous methods. If you have discontinuity between the different computational elements in your solution, which is non-C0 continuous, then you have discontinuous solutions. Within each element, you can increase the polynomial approximation. If you have high orders of polynomial approximation, then you will need fewer computational elements or fewer H. On the continuous side, if you have high H and low P, you are in finite elements. If you have more polynomials describing the solution, you will need fewer elements, so lower H, you enter spectral elements. And in the extreme sense of where you have the entire domain now being described only by polynomial approximations, you enter spectral transform. Similarly, on the discontinuous Galericon side, for high H and low P, you have finite volume. For intermediate H and higher orders of P, you have discontinuous Galericon. And finally, in the limit, it also converges to the spectral transform. So what are we essentially doing in these sort of methods? We have some sort of canonical equation where Q is a conservative variable, Q is a function of space and time. We then begin approximating this solution variable by putting an approximation function Qn, which is also x of t, and which has expansion coefficients psi and the basis polynomial. N here is the order of the polynomial. So higher the order of polynomial, more the number of terms we have in our expansion and in our approximation. So we can construct different sort of approximations. The mathematics of this is too detailed, but I will just give you a broad overview of it. So when we substitute the approximations into our partial differential equation, obviously this approximation will result in a non-zero equality because we have used a finite dimensional approximation. To resolve this, we multiply this approximation with a test function psi and integrate it over the small computational element and drive the residual to 0. We now partition this domain over different elements. Here an example is given for one-dimensional element, but ideologically this is the same for doing in higher dimensions. So here is an example of shallow water equations where we are looking at the free surface height, we are looking at the bathymetry or the depth of any water body, we are looking at gravitational acceleration, we have even put in the Coriolis parameter, we are looking at wind stress, and we are looking at bottom friction. This is really important for looking at models which look at tsunami propagation or storm surges. We then approximate this using triangular basis functions. Remember that we want to also look at complicated geometry. So here we have a linear interpolation or three linear functions which are doing the approximation at 3 interpolation points. So we have an n is equal to 1. We can look at quadratic approximations for n is equal to 2, and in case of triangles this will result with 6 interpolation points. If we go to higher order approximations like n is equal to 3, we will need more and more points to approximate it. Now, when we apply the discontinuous Galericon method to the shallow water equations, we then obtain the weak form. We then have something called as the numerical flux or the Riemann solver to communicate between the different elements, and in this case we choose the Ruzanov numerical flux. We then construct the matrix form of these semi-discrete equations. This is sort of the most important part because this is where we now are converting the PDEs into a set of algebraic equations. So we define each of these element matrices on an element by element basis based on the mathematics shown over here. Once we construct the matrix form of the semi-discrete equations, we can eliminate what is called as the mass matrix by taking its inverse and pre-multiplying it. Now we see that we have converted this entire system of PDEs into a whole bunch of matrix vector multiplies, which is exactly the form a computer likes and which is very efficient to solve on a computer. To compute this matrix inverse, it's a very small problem because we are doing this on an element by element basis. So for example, if we have a third order element and let's say we are doing it in 3 dimensions, the maximum size of this matrix could be only of the order of 729 by 729. This is typically the sparsity pattern for the discontinuous Galerkin method. Remember, if you compare it to the finite volume technique, this is far more dense. So essentially what we are trying to say is that data is much more local for the discontinuous Galerkin method. And this enables it to be extremely scalable. This is the scalability of a code called NUMA with a 4th order approximation using the discontinuous Galerkin method. You can see that this scales nearly perfectly well up to 32,000 processors. With 8th order polynomials, you can see the scalability is absolutely perfect. I could not show you data more than 32,000 processors because on the machine where this was tested had a maximum of 32,000 processors. So clearly this type of numerical techniques are very efficient. Let us recall that for finite volume methods, the scalability peak was about at only 2,000 processors. So this is essentially the discontinuous Galerkin method where we are now communicating between 2 elements, and to compute anything with some higher order of accuracy, we are doing things within each element rather than increasing the communication load. The beauty about this method is that you have more compute and less communication. So going back, this method is also very efficient on GPUs. So I can take the same matrix vector multiplies and offload it on accelerators much more efficiently. So if you look at the GPU speed up of these higher order methods, you can see that you can get up to 8 to 10 times speed up compared to lower order methods. This is without it being optimized on GPUs. If you further optimize it for memory fetches and other things which we have discussed in this class, you can even extract 25 times speed up at higher orders of interpolation. So this is another set of speed up statistics on Intel Xeon Phi, and you can see here you can get extremely high numbers of speed up over one thread by just optimizing these methods. Why is this important? Now let us go back and look at shallow water equations. We know that this is used to study tsunamis and storm surges. So we look at extremely large calculations like this 2004 Indian Ocean tsunami. So this is the picture of the bathymetry of the Indian Ocean, which shows the depth at different locations. This shows the computational grid that is being used for this simulation. You can see how fine this is, especially at the coasts, where I need to resolve the coasts very accurately. So this is the actual calculation of the 2004 Indian Ocean tsunami. You can see the earthquake originated somewhere near Indonesia, and you can see the waves going and hitting different parts of India and other parts of the world. You can see that primarily the east coast of India was affected, along with the coasts of Thailand and Indonesia, but the waves also reached all the way up to Africa and including the west coast of India. One question you will have is that how accurate are these simulations? So this is the representation of the same tsunami, but now with a 3-dimensional view, which shows the bathymetry a little bit in detail. So if you look at the data of the wave height and the arrival time of these waves at different locations in India, there was actually measured data, which is shown by the red line. The green line shows the predicted arrival time and arrival height. So we can see in Vizag, the arrival time and arrival height was sort of very accurately predicted. In the city of Chennai, the arrival time was predicted correctly, but the arrival height was sort of over predicted. In Goa, arrival time and arrival height was predicted reasonably well, and also in the Maldives. So it gives us enough confidence that this particular code is giving us reasonable data despite making several easy assumptions. Similarly, here is an example of a storm surge simulation in the Gulf of Mexico hitting the Texas coast. You can see the storm is going on a parallel axis to 45 degrees. And you can see how the surge develops as the storm is moving up. And you can see that you have increasing storm tides coming in way before the eye of the storm even comes near the coast. And you can also predict that the waves, the storm tides affect part of the coast where even the eye of the storm doesn't pass. Like far away from the eye of the storm, you will still have effects of the storm. The real problem that we have is an inverse problem, because real-time computing of any such event like a tsunami is a challenge. Even if you have the compute power, the uncertainty in the input parameters of where the earthquake is or where the storm is forming, this will not allow us to do these computes in real time. But it is essential for risk mitigation and disaster management. So we need to have an advanced knowledge of vulnerable areas, evacuation routes, strategies, etc. This is very important for government agencies. So what we really need to do is do a large set of these computes with all possible scenarios. And for that, we need large compute power. And so we need to figure out for each and every case what could be the potential scenario. And that's why we need scalable methods to solve these sort of large problems. So what we really need to do is develop inundation maps, look at vulnerable areas when we are looking at tsunami and storm surges. The current state of the art is to do 50 to 100 meter resolution maps, but we would like to see it at much lower resolutions. To do it at much lower resolutions means I need more compute power. The desired resolution for accurate urban calculation is around 5 meters. And we also need to incorporate complete information of urban structures. So doing this requires enormous amounts of compute power. That means we need to design codes which have to be scalable, which have to be efficient. So to summarize, to solve complex problems, we need more detailed simulation capability, which in turn requires more than ever computational power. Current numerical technologies has limits on issues of scaling. So we need newer methods like the discontinuous Galericon method, which promise to show linear scaling up to thousands, if not hundreds of thousands of processors. The idea here is that the numerical methods now have to adapt to newer computational hardware as they are getting developed, rather than vice versa, where we would develop specialized computational hardware for a specific problem. Thank you.